Okay, today we're going to go over what a limiting reagent is and how to find it. We're only going to be using moles, not grams. We'll do that a little bit later. This is a part of stoichiometry, but we also like to use a lot of food analogies when we talk about limiting reactants and limiting reagents. So we're going to do a food analogy too. Okay, so what is a limiting reagent? Okay. It could be also called a limiting reactant, by the way. All right, simple definition. It's the reactant that gets used up first. So proportionally, you have less. Oh, that's going to be a problem. And it basically determines how much product then, in that case. All right, that you can make. A lot of times people use s'mores as an example, and they say, well, yeah, it takes 2 graham crackers to make a s'more, and maybe 1 chocolate square, or however many you like to make, and a marshmallow. But those are ones that you can just really see, and they're pretty easy by just kind of looking at it and seeing how many s'mores you can make. Let's do one that's a little more complicated, okay? Let's do one where you're baking cookies, okay? So let's bake cookies. And let's say the recipe calls for 3 cups of flour. So I guess we can just say cups of flour. And it calls for 2 cups of sugar. And let's say about a teaspoon of salt, and we'll just leave it with that. Of course, there's other reactants, but we'll just pretend those are the ones that we're focused on because we have plenty of the other stuff. That's what the recipe calls for. So that's going to make 1 batch of cookies. Okay, so 1 dozen, let's say, cookies. And we want to make as many as we can, okay? That's the thing. And we want to see which one we're going to run out, which ingredient we're going to run out first, because that's the ingredient that's going to determine how many full regular cookies that we're going to be able to make, okay? Yeah, let's say we have 26 cups of flour and 15 cups of sugar and 9 teaspoons of salt. Now, technically, we have less salt than anything else, but in the equation, we only need 1 teaspoon. So the equation kind of tells you really the quantities of each. So you can't just by looking at it say, oh, 1 of these, 2 of these, 3 of these. You know, it's a little more complicated than that, slightly. Okay, so one way to do this is to see how much product each one of these will produce. And that's kind of what we want to know. We want to know how much, at least in this case. So pretend like we have 26 cups of flour, and then we have infinite sugar and salt. How much would that 26 cups of flour be allowed, would allow us to make? Okay, so how we do that. Start with what you have. You have that 26 cups of flour. And then multiply by the ratio of how many dozen cookies you're going to be able to produce versus how many cups of flour you're going to need. We're going to need 3 cups of flour. Those are in the same units, cups of flour. And we're going to make 1 dozen cookies. That's your, kind of like your molar ratio. All right, so we need to do 26 divided by 3. Oh, I think I did that. Hang on. I did times 3. And I get 8.67. And that's okay. We're going to just say that's how many dozen cookies, right? So if you have 15 cups of sugar and we had infinite supply of everything else, we'll figure out how many dozen cookies we can make, okay? So looking up here at our equation, you got to look at these coefficients, these ratios. These could be molar ratios too. We have 2 cups of sugar is going to make 1 dozen cookies. All right, so we have 15 divided by 2. All right, so we got 7.5 dozen that could be made, which is less than we could make if the cups of flour was the only limiting reactant. But it's looking good for sugar being the limiting reactant. But let's make sure. Okay, 9 teaspoons of salt. And in the recipe, we only need 1 teaspoon of salt to make 1 dozen cookies. All right, 1-to-1 ratio. Yeah, we could make 9 dozen cookies. I don't know why I spelled it like that. That's fine. Okay. We know since the 15 cups of sugar is going to make the least amount of cookies, that's your limiting reactant. The flour and the salt are what we call excess reagents or excess reactants because we have them in excess. They aren't the limiting reagent. Okay. So let's just do a little bit more of a chemistry problem, specifically, just to see how that can also play out, and a slightly different way of doing it. You can do it exactly like this in your chemistry equation. You can pick a product and see how much of each reactant it makes. But if we do combustion, and I picked decane just for funsies, okay? I know we haven't learned that in our chemistry class yet, but deca is 10, and we're talking about carbon organic compounds, and the A-N-E ending means there's single bonds between these 10 carbons. So I just thought it would be fun when I ran out of space to just kind of see, well, you could figure out the formula. One more. And you'll know how much hydrogen, because each carbon atom wants to share its 4 electrons. And in this case, it would be with hydrogens. So that's how many hydrogens you would have. All of these little sticks would represent hydrogens. And if you count them up, it'll be 22 hydrogens. So the formula for decane is C10, because 10 carbon and 22 hydrogen. Now, if you combust something, you just add oxygen to it. And of course, since it's just a hydrocarbon, you're going to get, or a carbon-containing compound, organic compound, you're going to get CO2 plus H2O. Okay, it's not a hydrocarbon. It's okay. All right, so we've got to balance this because there's only 2 oxygens here, but like everything else we've been doing with combustion, leave the oxygen for last because you can always adjust that at the end, you know? And I've been doing the rainbow method, so just to review, it's another way of doing it. I have 10 carbons here. I noticed I need 10 here. Yeah, put 10 as your coefficient. Leave the oxygen for last, and since I have 2 hydrogen here and 22 over here, I need 11. Sometimes it just helps, you know, connecting them. For oxygen, then that means we have 20 over here plus 11 over here, and we get 31 oxygen total when we only have 2 here. So that's why we're going to adjust it here. Unfortunately, we have to figure out what times 2 is 31 because the oxygen is diatomic and there's 2 of them. So here's how you do these. Tentatively, I could say half of 31, gosh, it's 15.5. So put 15.5 down there as our tentative coefficient. We don't like leaving it that way. I mean, technically, you can still do your homework that way. It is balanced technically, but you can't really have 15.5 oxygen molecules. So what you do in this case, of course, is just double each quantity. And those would be the real true coefficients. So there's nothing here, so it's actually assumed to be 1, so we put a 2 there. The 15.5 would go back to 31. The 10 would go to 20, and the 11 would go to 22, okay? And those are our coefficients of this balanced equation, and we're going to use that to convert molar quantities of one reactant or a product or something such as that, okay? So classic example, we're going to say we have 1.75 moles of decane. And let's say we limit the amount of oxygen and we only have 26 moles of O2. Now that's weird because if you were burning decane, in the open air, you'd have unlimited supply of oxygen and automatically your decane would be your limiting reagent. But since we told you we have 26 moles of oxygen, we're going to assume it's not in open air. And one of these is going to be the limiting reagent. Okay, so one way we could do this is to see how much of one of these products we could make. We could convert decane to CO2 by using the 2 to 20 coefficients. Or we could take the the oxygen and convert it to CO2 also. That's two different conversions. You'll still be able to figure out which is limiting reagent that way. But another way to do it is to convert one to the other. All right, let's pick one. Let's convert the 26 moles of O2 to see how much decane would be needed to react fully with that 26 moles. Okay, so we're going to convert moles of O2 to decane moles, C10H22. Cool. So we got 26 moles. Remember, start with what you have. Put the units down. Straight lines are hard. Use the coefficient here. I have 31 oxygens required for every 2 decanes. Put the oxygen on the bottom. That would be the 31. And we're using molar quantities, so we can say 31 moles of O2 would need 2 moles of decane to react with that. Okay, so then we would multiply across. The units of oxygen cancel out. And we get 52 over 31. And use a calculator. You can make that simplified. 52 divided by 31 is 1.68. Rounded moles of decane. Now, you're not quite done yet. You need to compare the quantity of decane you have with the quantity of decane that you would need to completely react with the 26 moles of oxygen. It's a smaller quantity. You notice 1.68 is smaller than 1.75. So your O2, you're going to run out of that first. You can only make 1.65 moles of decane with that 26 moles of O2. Okay? This kind of makes sense. Another thing that you can do is you can figure out how much of one or of a product you can make with the reactant, or you can find out how much reactant you're going to need to make a certain amount of product. So let's just do that really quick too. Let's just pick a weird number. What's a good weird number? Let's say we have 78 moles of CO2. Okay? That's what we have. And we want to find out how many moles of decane we're going to need to react with that. Okay? So yeah, this is just a review kind of converting. Put your coefficients here. I get a 20:2 ratio of CO2 to decane. Yeah, you could have changed that to 10:1. That's a fine too. Multiply the tops, and let's see, you get 78 times 2, 156, divided by 20. And that'll give you, because these units cancel out, you get the moles of C10H22 that you're going to need to react fully and form that 78 moles of CO2. And if this is in the open air,